So let's get started. Just a gentle reminder that homework 1 has been released, and it will be due like I think after the holiday, so 3rd of October, and some of you actually look for me and ask me in particular question too, right? The maximization problem, the profit one may not exist, right? That because of this function f is increasing with terms of scale, right? And in that case, these are not really well defined. But I was intent to try to see if you know or not, but someone asked me, then I reply, so I have to tell everyone that's the case. I mean, try to see if, but that being said, this ABC still is well defined. So actually, that is the reason why I want to give this question, is try to let you know why you want to separate two parts, is because of even this is not well defined, ABC is still well defined. Okay, but it shouldn't be any issue for the consumer. Okay, but anyway, you can try and see if you have any question. So let's continue our journey on equilibrium today. The goal is to finish the whole topic. The goal, as you can see, is pretty ambitious. We try to cover the partial equilibrium. We've just finished the perfect competition, but we'll look at the monopoly, Carnot, Bertrand, and monopolistic competition. I would say this is the most useful technique that you use, and I can tell you, right? Many of my research actually rely on these models, and if you able to carry this long enough, then I mean a lot of things can be done. I mean, of course, you can't really do it with the top 5, but you can easily apply to your model, right? Especially when you look at this application, say look at operational research, look at accounting, look at finance, and this basic model is well accepted, and you can still use it. And people still put it in the top journals, and even recently they still look at Bertrand and Carnot. Of course, they have more stuff behind, but I mean these are the basic model. And for general equilibrium, and I don't think any one of you would do theory on that. But some of you who have background in finance or do asset pricing, you'll be touching some of the issue there. So I just scratch a little bit of surface on that, because the textbook treatment will be way more complicated than I do here. But since most of you are not using anyway, so I just briefly tell you what's going on there. So to review what we have done last time is we consider perfect competition. And that's homogeneous good, that's same good, every firm for the same good. And that means that we have something very simple. And we have just saying that very simple model because a single good. So basically just demand function is just P given Yi, right? So abstract, right? Of course, you have demand for all the good, but it's abstract by this Qi, right? Because you form a Marshallian demand, right? By looking at how this trade off the others, right? So basically, other goods are holding constant the prices, right? So you can imagine there's a P for other prices, but subsume here because the price of other goods doesn't change. Okay? Just we consider there's no repercussion for this market, right? The price and quantity change in this market, right? It's not going to affect the other market that has a feedback effect, right? So basically just this market is small enough, we can assume this kind of analysis is right? If not, then you have to analyze simultaneously multiple market together. right? That's why the supply chain model, right? You not only take the upstream, downstream at the same time, right? So, or same as financial market, right? You can't focus on one single asset. You have to focus multiple assets. That the problem is how big is your analysis. Depends on, of course, empirical, but also from your judgment whether these several market you at the same time will be relevant, right? But later you see when we build the Cornell or Bertrand, what kind of this things should be incorporated into your study. Okay, so just to aggregate the individual demand and get the market demand. Okay, and here I subsume all the problem, just the summation, right? And I just highlighted it's not the sum of the income, but rather the distribution, and area income matters, right? And I also don't mention, actually, this is a big problem in economics, how to do aggregation, because this has a nice property, right? Saying that the price P, right, is going to be inversely related to quantity, right? The downward sloping demand is guaranteed, but this is not guaranteed in aggregate, right? Because there's a price change in income effect, substitution effect, right? And in you aggregate, it need not be, I mean, the standard normal demand curve. Okay, but by writing this, usually this is we start, right? When we write the model, usually we don't model individual, right? Usually we do represent the consumer, that everyone is same, and we model in this way, right? But do note that when you actually apply to practice, that can be a little bit issue, right? Because when you have two groups of consumers, say, right, and they in aggregate they may need not follow the standard one, right? Each group may be following this nice property. When they add up, they need not be. Okay, so then you have to decide how to group your consumer, how to separate them. Then can be part of your model specification. But in this one, we just make our life easy, right? And the firm the same, you just say single supply, because we assume it's homogeneous product, then this thing will be easy because the supply function can simply add up, right? Because there's no difference between the product produced by each firm, right? Of course, if this is not the case, then we will be careful, right? We'll do it more in the game theory setup, but you will see here everything you just add up, simple, right? Because if good by different firm is not homogeneous, not the same, you can't simply just add up, right? Different good mean different thing, right? Even if you have a different color, can be called a different thing. What the same or what not the same can be a little bit issue here. Okay, but we make our life easy to assume every firm will do the same product, so we can add up. Okay, so that's is the equilibrium. We have aggregate demand, market supply, and then it is where that the equal, right? And do note that in this model, the income and the input prices are exogenous, right? And do note that this is what the general equilibrium is about, is try to find other market that make everything is endogenous. Okay? This we'll talk about a little bit at the end of this slides. That we'll talk about general equilibrium, the second half of that. And just remind you, this is the in the short run, you look at the short run AC and short run MC curve. Firms are making profit. And why short run? Because no firm can enter exit. There's some fixed cost here. So that means that they're making short run profit. Okay, and actually they can be losing money. So have to be careful about here. Okay. And when you long run, can be end a lot of things, but in this model, we just assume the long run is make endogenize the number of firms. Okay. And you can, as I said, right, you can do this without going to general equilibrium by incorporating, say, labor market, right? W can involve labor, and you can have a labor market there, or W can involve raw material here, and you have an other entry exit condition, right? Depends on what you think is appropriate. Then you can extend this model, right? If you extend norm big enough, then it becomes general equilibrium model. But this is still partial equilibrium if you have something remain exogenous. Okay, so then the long run will be like this. Okay. So I have when I write 0, actually I have some assumption here. The hidden assumption here is there's no entry exit cost, right? If entering the industry required to pay capital fee, you need a huge factory, right? Then you should be more or less than that amount, which license fee, right? You have to enter, or exit, you have to pay money. That will be bigger than negative, right? If you exit, say in China, now you have to close the factory, you have to pay all the bill before you can go. All right, so you have to bigger than negative of something. So it really depends on the nature of the problem. But you can see this rather fixable. And sometimes you find some of the literature in business, finance or business, they do impose more condition they think is appropriate, right? Maybe they think there's a price control, you can also do it here, right? Suppose there's a P that there's a price control so that they cannot adjust lower, upper, there's tax, so on and so forth. There's some constraint you can also add there. But here in the equilibrium, in the standard framework, with the long-run equilibrium, competitive equilibrium, or perfect condition, it just state that price equate the two. Okay, but that is the assumption of the model. Okay, now we go to the other extreme. Okay, we go to the one extreme is perfect condition, where no one have market power. We go to the other extreme, where only single firm have all the market power. So consumer market price taker, but the firm is having all the power to set the price. Okay, this is you often use in modeling because we don't want to complicate ourselves with the strategic interaction. Even if you think there's a duopoly, you still want to look at monopoly pricing because that usually that would be giving us the most of intuition there. Okay, so it's still a single firm that has single product. Okay, you can generalize the multi-product. That would not be difficult. So the assumption here is they face the whole market, right? So we assume directly there's a market demand function, okay, is downward sloping. That means that we can invert it to have upward sloping, okay? That's assumption, okay? We always start with that. And this is, we start with the inverse demand. So usually look at the paper, most time you start with either this or that, okay? And they do it interchangeably. But downward sloping is not a big deal, but we just assume it. And here we need to define a very important concept we call elasticity of demand. Why is the case? You will never understand it when you do to empirical. The reason is you're never able to understand the whole demand curve. The best thing you do is to look at this elasticity of demand. That's how what actually applied people do. It is how you can estimate. You can never estimate the whole demand curve. The only thing you can do is the elasticity. And by doing it, you just take a log on the both sides, right? You have the quantity and the price and take the log, and then that would be demand curve is you can estimate. Of course, there's a lot of econometric issue here, but assume you can do it, then that is what you can do, right? Because there's when you learn econometrics, there's a simultaneity here, but I'm not going to talk about that. But assume you can do you have some kind of nice data, you can estimate that. That's estimatable. And that is very simple, right? This definition just saying that percentage change in price lead to how much percentage change in Q, right? Suppose elasticity 2, that means that 1% change in price lead to 2% change in Q. right? If 1, then the same, right? 1 to 1, right? If half is like the same, right? So this is follow the standard of idea from physics, right? Elasticity of an object, right? So how much force you apply, how much it extends, the same as the concept there, right? Whether 1 is not 1, then you learn in the microeconomics principal class, right? When it's elastic, right? That means that the absolute value is more than 1, right? Because change in price leads to much more change in the demand, right? So that means that this is the very important thing you learn in the undergrad, right? If the demand is inelastic, you want to increase the price, right? Because P times Q, right? So the percentage change in the revenue is percentage change in P plus percentage in Q, right? Take the law, right? So if it is elastic, then you want to reduce the price. Inelastic, you want to increase the price. That is what you're going to do. Now, so why this is important? Because this is also important in antitrust or all the other analysis when you have monopoly. So technically, as a monopoly, you can choose both price and quantity because you face the whole market, right? But because of downward sloping demand, choose P and Q the same as choosing Q or choosing P, the same thing, because there's only one thing you can do, right? So that's why usually you can write this revenue minus cost. Assume it's cost function here. Remember, this is the cost minimization problem, right? Right? This C of Q is the cost minimization problem. You decide the quantity, right? And then how much the cost, total cost, this condition, right? And you can do this, choose the price, which maximize this profit, right? Also the same. Either you focus on the inverse demand or use the demand function, right? Because P of Q is the inverse demand, okay? Either way we do, and doesn't really matter which one you use, okay? The same result should see. And of course, when you think the firm later, you see when the firm compete in quantity, this is what you do. When firm compete in price, this is what you do, right? Depends on which kind of modeling in your model. And later we'll discuss when you think the firm are compete in price, when you think firms compete in quantity. But for the monopoly, there's no difference, right? Because they face this. For the marketing people, they will actually think it's where they think quantity. They think in price, right? They were saying set this price, this number of people would come in, right? Because this, but actually the same thing, because the face downward sloping demand, you set the quantity same as in price. So even though you have a marketing department, actually there's no difference because of facing downward sloping demand, right? If consumer behave in this way, okay. Now we are going to look at the optimal production level or optimal pricing. Usually you will see the Q, okay. Why? That is easier to look at the result, okay. And this is a product rule, right? Because P times Q, then you take the Q and take the P, and then there's marginal cost. So the important is FOC, right? The FOC is the marginal cost, is the right hand side, right? It's equal to marginal revenue, right? What does the marginal revenue looks like? Okay. There's some explanation here. The first term is what? The first term is you try to produce one more unit, right? The right hand side, sorry, right hand side first is how much it costs you, additional cost, right? And this first term is if you produce one more unit, you sell at the same price, okay? That would be that's K, right? Suppose you can sell at the same price. This is what you would get, right? But the problem is the demand is downward sloping, right? In that case, this is negative. The first derivative of P over Q, right? The slope of the demand curve, right? Because you increase the quantity, have the price reduction, then have to go into your quantity, right? Because for each unit you used to sell, you would have reduction in price, okay? So that's why this is the reduction in the price you have been selling before. First is You produce one more unit, you can sell that unit. This is the extra revenue you get. But there will be trade-off because you sell one more unit, then you can't sell at the same price as before. You sell at a lower price. And this is a reduction in revenue because of additional unit you're producing to the market. Okay. Let me repeat because this is important. That you will have to write in your model, right? Although in general, you have more different structure of the demand, right? Suppose in this model, we have a very simple demand curve, right? But you can imagine there's a network that may be very complicated stuff. At the end, this is the same, right? It's just only the C function and P function can be very complicated, right? But no matter what kind of structure in your model, you always get marginal revenue to marginal cost, right? As first order condition, right? As long as this is satisfy the SOC anyway, right? Second order condition, right? Suppose this is convex and this is a nice property, then this FOC will be the optimal condition, right? And at the end, right-hand side is marginal cost, right? Can depend on many things, but this is the model, right? And MR will be additional unit you sell. This is the revenue generate, and existing unit you can sell at a less price. Those is this thing. Okay. So you can easily see why this is optimal here, right? Because if this is the left-hand side is bigger, then you produce more, right? Because revenue more than cost. And if this is the right-hand side more than left-hand side, then you will sell less, right? And why this is not sufficient? Because there can be local max, right? Or local minimum there, then you cannot ensure. But as long as your cost is convex, then this is almost like guarantee, right? And usually we assume the cost is convex, right? And the demand is well-behaved. Okay. By well-behaved, you can check the second order condition, right? And for application, usually assume the SOC is satisfied by definition. So we can rewrite this. Okay, it's often you see this in the application. Okay, is we rewrite the left-hand side, which is P plus Q P prime, right? You just we write this elasticity, right? Because this is Q, right? You take the P out, take the P out, okay? Then 1 over Q over P, okay? This is P dP dQ, right? So this is this one, right? This is a P prime. Okay, take the P out, okay? Why I want to write that? Because this is inverse elasticity, right? Because elasticity is dQ dP, right? So just reverse it using the inverse function theorem. So that would be this formula like this. That means the marginal cost and the price are related by elasticity. All right. And right, sometimes this is called the markup, right? The markup. Later we'll have a next slide to tell you. But that means what? Okay, that had to be first, right? This is a positive number, right? So the whole thing has the positive number, right? So this is negative, right? It could be negative, right? So this negative number cannot be less than 1, right? Less than 1 because the whole thing will be negative, right? So this thing must be, this absolute value must be larger than 1, right? So it means that monopolies must be working in the elastic region, right? But that is easy to understand because they increase the price until you can't increase, right? So that would be the first thing. Of course, this one is not frequently used directly. The more frequently you will see this one. You can rewrite that, right? P minus C prime is this one. Okay. So this is often you will see in macro. If you're doing macro class, this is often you will see. Okay, the macro class will say this is the price minus marginal cost. Is the markup. Okay, and sometimes they call this relative markup. This is absolute markup. Okay, this markup is inversely proportional to elasticity. right? And this is important because in macro literature, they will say why have business cycle if this markup changes. Okay, they look at the business cycle, GDP move up and down, and actually they look at data, look at how firms markup changes. They figure out that they are very they covariate a lot. So that's why they will say, okay, why business cycle? One of the reasons is the markup changes, and you go back to microeconomics. Why markup changes? Right? It must be either cost fluctuate or the price actually fluctuate. Right? And of course, that will be another thing. Right? Right? And right. And yes, you can see, right, this markup, right, is measure elasticity, right? And somehow elasticity is the market power of the monopolists, right? Right. And how can we measure this? As I said, right, it's very difficult to measure this guy, right? Suppose you regulate a monopoly, like public company, right? Power supply or water or whatever, or SpaceX, right? There's no competitor, right? And how can you measure the elasticity? It's very difficult, right? There's no way you can that easy, but you can do this one. The left-hand side can be done easily. You look at the price, you can see, right? Marginal cost, somehow you can see, try to estimate, you can have some idea, right? By having that, you can look at the elasticity, right? So that is the one way that people try to estimate elasticity, because this can be done in this way. The left-hand side can be done, right? And by looking at this, then you can probably imagine whether the firm has higher market power or not, right? Because elasticity of demand is supposed to be stable, right? Shouldn't be changed a lot, right? But if markup fluctuate a lot for, say, water company, they may be actually abusing, right? Suppose the firm merge, right? Maybe two public company merge, or water supply or electric companies, then the markup increase a lot, right? Then it must be the case the firm is actually abusing the market power, right? Because you would not imagine that the water supply, this thing, or electricity actually change a lot, right? So that would be the thing, or the markup increase a lot. Actually, the firm actually are getting much better advantage, right? Anyway, I guess monopoly we have done, but although it's very simple, but you will see many complicated model will be the same framework. So if you have you build a model, right? Usually what you would do is not that simple, right? You would be, although at the end you have the same formula, right? But this function may follow up according to your model. Say, suppose the finance model, you may be taking into some financial factors, right? Maybe some policy changes or some financial structure. You change this guy, right? And say the P maybe depend on supply chain, depend on network, depend on marketing campaign you're using, right? So that will be changed, right? And then you can look at how this model behave, right? And then you can imagine there's a government there, right? If the government try to change taxation or change the policy, right? How it affect the market, right? You can consider the government actually care about the social surplus, or care about consumer surplus, or care about the markup. That is how you can write your model in that way, right? So even though this is kind of simple, you can easily imagine there's a lot of way to generalize this model according to what you want to study. Okay, so although we teach very basic model, but everything can be easily extendable in a short period of time. And next one is the corner model. Probably I will say this is the most important model when you do the IO. I mean, besides Bertrand, because Bertrand is so simple, I don't think we need to study anyway. But this is a little bit the model that usually use. Okay, and I think it's the most common. You go to conference, basically this is the one that people would use it. So because there's so many people use it, then this one is well studied. There's a lot of paper on this. Okay, and this model is saying that firms are not competing price, are competing quantity. And this is the case when we talk about the crude oil, right? The OPEC, right? OP. The oil exporting country, actually, the oil very similar. Homogeneous good, they just basically compete on quantity. No one have price setting. And when you talk about agricultural product, they compete in quantity, right? And what else? No, right? You would not think iPhone is competing quantity. Apple is no, not really, right? They compete in price. Okay, but later you will see that actually it's not. When you allow heterogeneous product, they didn't difference a lot. Still, you can apply still the Column model variant type. When you consider, say, the company price, the company quantity, model will be different. But you can imagine competing quantity is like a long-run competition. Okay? Because there's a model to justify why firms compete in quantity, just like they will do it per chart in the second stage. The first stage, they are competing in building up the capacity. Right? Later you will see per chart model is everything go to marginal cost. Okay? Later you will see. But that is too extreme result. And this is the result that we used to like. And this result is used to be the one that's good. Anyway, in this model, no one have price setting power. Okay, and I said in our class we focus on very simple setup. Of course, easily generalizable. We use the linear demand, constant marginal cost, and zero fixed cost to make our life easier. But they are easily can be dispensed with. Okay. So as I said, we focus on easier one with a linear demand. Okay. So when we have linear demand, then we have linear inverse demand. Okay, which come from this expression. And the question you ask, okay, why you start with this one, right? And is there any utility function that follow this one, right? Because you learn topic 1, right? We said we shouldn't start with the demand. We should start with utility function, right? The question would be, is there a utility function behind this? The answer is yes. There's a paper recently, not so recently, but 3 to 5 years ago, that tried to say when you have contracted utility, you will have this. So you can imagine if you are a site engineering person, this approximate, there may be a approximation to the demand. Okay? Linear approximation to the demand, that would be an appropriate assumption. Okay, and don't worry, in most business application, this is no problem. But when you go to economics, then maybe some issue here, you have to defend it. But in general, this is okay. So homogeneous good, so that's why I can add. Okay, and they use the same coefficient, right? Because they're homogeneous. Okay, if not, they have to come up with multiple prices. So suppose our life is easier than making this one. So the J firms, now do note that the J is exogenous given in this model. J is not endogenous choice. Okay? And each firm has constant symmetric marginal cost, small c times qj. Okay, and there's no fixed cost because it's marginal as same as the average cost. Okay, so then this would be the profit function for each firm. This is the price. Price is linear, so it's A minus all the quantity times its own quantity, that's revenue, minus its cost. Okay, so very simple. Okay, there's nothing very deep here. Okay, and you do note that the price is contrasted to its own quantity, right? So you would have a solution. Okay, and what Carnot model do? Okay, or actually before Nash, is the Carnot thing is in this way. So what is the equilibrium in this world? right? There's an issue of equilibrium or what is the outcome there, right? In the perfect competition, the equilibrium is such that demand supply equals the same, right? And in this model, okay, the demand function is given, right? So whatever firm can produce can be done, right? And then because price is endogenous, right? So there's nothing the price that equate the demand supply, right? Price always equate demand supply, right? So there's everything is equilibrium. So how can you say what's equilibrium here, right? So that is what the Carnot suggests. What would the equilibrium here is at that production for each single firm, okay? No one want to change the production, okay? Suppose firm 1 produce 10 unit, firm 2 produce 20 unit, okay? Only 2 firm case. No firms want to change its plan. Firm 1 want to stick with 10 production. Firm 2 want to produce 20 unit. That's it. Okay? It's just saying that given other people production, I don't want to change. Okay? That is the equilibrium. It doesn't say this is the best for both firms. It's not Pareto optimal. Nothing is being said, but this saying that in that particular production that we assign to these 2 firms, no one to change. That means that there's can be more than one equilibrium, or there can be no equilibrium. Okay? Because it's different from the adjustment from the perfect competition, right? There's a price adjustment, right? If the price is too low, okay, and firms will not produce, right? Then supply drops and then the price goes up, right? And so forth. There's some adjustment. This one, we don't provide any adjustment process. Just saying that, okay, there's certain production by each firms so that they don't change at all. Okay. Then later you will see this idea behind Nash, but actually is invented long term back by Carnot. Okay, which essentially said, I produce this, you produce this, okay, and no one changes. Of course, in some cases you can see the adjustment. Okay, say if I produce 10, you produce 20. Maybe you think you produce too much, then you reduce to 15, and you do 15, then I can increase a little bit, and then maybe there's some adjustment. This adjustment process may exist in some model, but not all the model can do it. Okay? So whether the equilibrium is robust, I don't know, right? Because you can imagine this equilibrium, maybe there's some slight changes, you go to this equilibrium. I don't know, there's a dynamic property, it's not ensured. So just saying that this at this particular point is there. It is possible that you deviate a little bit, then everything destroy. Okay? But that is a definition, right? Is every firm is maximizing its profit. No one wants to deviate from that outcome. That would be the equilibrium, which we will use it in the game theory in great detail. Okay? Okay? But we'll prove this result. Okay? This will be a simple proof. We'll go in detail because I want you to know how to do it because we do it in game theory as well. So let's do carefully how to derive this formula. But at the end of the day, what you will see is how much to produce is A minus C. A is the intercept of the demand curve over B, which is the slope of demand curve, over number of firm, and this is the price. Okay, will be that. Okay. The important point now I want to say is how to interpret this because we can derive the model, but we want to know what does that mean. Okay. First, you can see how much you can produce is inverse related to C, right? The more costly to produce, the quantity you have less, and the price is positive, so you have more C than P is higher, right? This is how you would have to write in your paper, right? So because you are going to, when you always try to work on the model, right? You're not going to follow this one, right? Your model can be more complicated, right? Imagine you are writing your model, will be, okay, maybe more parameter there, right? Or that structure is more complicated, right? Once you derive the model, you solve the equilibrium, right? Actually, no one cares about how you derive it, right? I mean, in the appendix, of course, They'll care whether it's correct or not, but no one cares how you derive it. You may spend thousands of nights to solve a complicated formula, but no one cares about how you solve it as long as you solve it right? Only care about your result, right? So that's why the first thing to do is do compressed statics to make sense of it. Okay, see if C goes up, what happened to the Q? Does it make sense? When C goes up, P goes up, right? When C goes up, Q goes down, makes sense, right? Second thing, look at A, right? A is the demand, right? Because downward sloping demand, A is this where the price is zero, right? Because A, go back to the beginning, A is what? A is the one that where no one produces anything, the first unit, how the market will pay for that. Okay. A is measuring the size of the market in that sense, right? If this is given, no one is producing the first unit, so the most hardcore friend would pay for that. Okay. So it's proxying the size of market, you can say, right? How big the market is, or how good the market is, right? That is very simple, right? A is bigger, then Q is bigger. A is bigger, P is bigger. Pretty normal, right? And A minus C is measuring this how efficient the market is supposed to be, right? When C is bigger than A, then the market collapses, right? So by definition, right? If A bigger than C, you cannot go to negative, right? So that if equilibrium exists, A must be bigger than C, right? And A is higher, P is higher, normal, right? More demand, more price. Very normal thing happen. Now look at the B. The quotient B would be B is higher. What? J is lower, right? Why? Because B is kind of elasticity, right? Or the slope of the demand curve, right? This demand curve, right? In B, right? It's how sensitive the people are, right? And when people don't like it that much, then this, right, will be different. Okay? Now look at the J. That is nothing with deep here, right? Because it's dividing the market, right? If more firm, each firm becomes smaller, right? And for this one, what happened to when you have J is more? Can you see that? You can take the derivative. Okay. Is it J monotone or J increasing, P increasing in J or P decreasing in J? Any clue? Did I write that down here? Yeah, I did. Okay, maybe I just talk about here. I'll talk about the proof later. But let's see this one, and we have a break. And after the break, we can talk about that. But let's talk about this one. Okay, first look at the markup. Markup is always equal to J plus 1, right? Then it's not surprising when J goes up, the markup goes down, right? More competitive market, this one goes down, right? And you can easily see that when J go to infinity, what happened? P star go to C, right? And that means that we have a perfect competition outcome when J go to infinity, right? So that's why when you learn the principal class, they say, oh, there's infinite many firms or many firms, and perfect competition will be achieved, right? That term actually, the idea that's actually coming from Carnot idea, right? Carnot said when homogeneous market, when you have many firms comes in, firms are symmetric, right? In the particular case, and actually the price actually go to marginal cost, right? So even if they're not price taker, but because of every firm is getting smaller and smaller relative to the market, that you have that. Okay. So now go back to ask the same question here, right? When J goes up at the end, this thing will go to C, right? Because you would take 1 over J here, 1 over J here, right? Take infinity, right? So That's how you can take this one. Okay. After the break, we'll talk about how to derive this part slowly, because this is the part that I want you to know how to derive it. Because we're doing game theory, it will be the same. Because the coordinate equilibrium, that's we're doing partial derivative. We'll go slowly, part by part, how to derive that part, and how to derive the result. It is something that we want to do after the break. Okay, but before the break, is there any question? Although we have a very simple model, right? But as I remind you, it's easy to adapt the model to the things you want, right? Say, suppose now I only have quantity, right? You can extend the model to some other thing as well, right? Besides quantity, they may change the feature or quality, right? And the demand will be not in this simple format, can be other way around, right? There are many things you can change to the model, right? To make this would appear, right? Because no matter how you complicate the model, you would kind of like a downward sloping demand anyway, right? So, but of course, this form may not be that simple, but everything can be done in pretty straightforward manner. Okay, so we will do the derivation after the break. Let's have a 15 minutes break. We'll resume at 1:30. So none of you will reply, but I just still put here in case you want to reply. Because given the past experience, you don't have any feedback, but just in case you want. We'll resume in 1 minute's time. Okay. Guess no one would write as I would expect. Unless I'm into right. Yes. So let's get back to here. Let's actually derive the equilibrium. We will be actually asking you in your assignment to actually deriving equilibrium anyway. So let's do that. Okay. So how do we solve the equilibrium, right? The equilibrium will be such that everyone is doing the best given what other people doing. Okay. And it's concave, so actually you can take the FOC, right? There's a product rule here, right? You differentiate this, the left right-hand side is this C, right? The left-hand side with this guy, this product rule, right? And you have that, and then this point, right? Right, because when you differentiate this, then you have this guy. Then we'll go inside this guy. Okay. And actually you can see the FOC will be system of linear equation, right? So you must either have one solution or no solution, right? Because there's a J equation, JQ, right? There's a linear equation, linear system, right? By matrix algebra, then you know you can actually solve it by solving the Cramer's rule or whatever, invert the matrix, right? But there's a better shortcut to here. You just sum all the FOC together, you get this one, because the J FOC, the J of this, and sum of all the Q is the big Q. Sum of all that will be is the big Q, so it's a JQ, and then see this and can solve the error quantity. Okay? This is usually the shortcut for solving linear model. And once you have that, this can replace, go back to here. Okay. Once you solve this, you can put this back to this. This is big Q, right? You can plug it back, right, like this one. Okay, this is Q. Okay, and you figure out that this is A minus C over BJ plus 1. Okay, and once you calculate the quantity, you can put that back, and then you can get the price. Okay, and this is how you arrive this solution. Okay, you expect to know how to solve this example. Because this is green, right? I mean, you expect to know how to solve this particular style of model, okay? And this is one of the main objectives of this class is let you write your own model and you solve it, right? So that's the one of the goal of the project, right? If you want to do it, you will be something like this, right? You will be probably adjusting this model a bit and see if you can figure out how to work it out, your solution. Okay. And I have to remind you that here is linear, so everything this is sufficient to guarantee it's optimal. It's quadratic. Okay. And when your case is general model or you have your own addition, either you make assumption that maximum exists or they may have corner solution. Right, so have to be very careful when you write your own model, write your new thing. That may be a corner solution. So either you check the second order condition, right, or you just make assumption there, right, that will be there. will be true. Okay. Now I think it is okay to have a quantity competition, and I think that cover 80% of the application that you ever think about firms are competing. The other 20 to 10%, almost remaining, will people focus on Bertrand competition, or people know as price competition, where people are choosing price, firms are choosing prices instead of quantity, right? Which probably would fit our intuition better. Okay. And price comparison is easy when goods are perfect substitute. Why? Because your demand function will be somewhat discontinuous in price. Why? Your utility is adding every, say, X1 will be good by firm 1, Xj will be good by firm J. Since they are perfect substitute, what is your utility maximization problem? It's not defensible, right? Remember, so you cannot really have FOC, right? How the marginal rate substitution, right? Because that is some issue here. It's not strictly quasi-concave, right? So that is an issue, right? Because combine anything that is indifferent actually is not better, not strictly better. So there's no unique solution, right? I mean, there's something that there's some issue here, but turnout is not easy to, it's not difficult to see, right? What you're going to consume is choose the lowest price and buy as many as you want to, because everything's same to you. You buy the one the cheapest, right? So that would P star with the price that's lowest, right? And then your demand will be like this, right? If the price of your price is bigger than the minimum, okay, then this wouldn't work, right? You will not buy anything. If your price is lower than the minimum, excluding you, right? Your firm J, right? The firm J is your price. This is the minimum price of all others. It's lower than you, then you are the only one, right? You get the whole demand, right? And if there's someone same as you, then you even the dy. Okay, this is a edge. This is knife edge case, but how you split doesn't really matter. Just there's some division there. This usually is not important for application, but we just assume equal sharing, regardless of what. Okay, so that means that mathematically it's like complicated, but the English is very simple, right? So goods are the same for every firm. For the consumer go to buy the represented consumer actually will go to the lowest price. If there's one, if there's more than one, they will equally split between firms that's lower price. Okay, and in this one, okay, assume there's a constant marginal cost, right? And the profit function will be like this. Okay, that is just minus the C there, just very simple. So the question would be, okay, consider the same Nash equilibrium, okay, with saying that other firms have their own price, I set my price. Okay, given they're not their price here, I'm not changing. Same with everyone. What is the Nash equilibrium? Okay, and this they are choosing the price. This equilibrium turns out to be called Bertrand equilibrium. Okay, it's a Nash equilibrium, but in terms of price. Previous one is quantity. Okay, and turn out to be, not surprisingly, but probably you know that when you learn the undergrad, the principal classes, and this outcome, even there are two firms, or how many firms you have, the only outcome that's possible is price equal to marginal cost, C. Okay, and what surprising result, right? Because you would think if there are two firms and three firms or four firms can be different from our understanding the real world, right? But when they compete in price, end up in this one, right? So that is something that is economists are uneasy with that, because we would think that why, right? Why this is true, right? Of course, it's easy to prove why this is a out equilibrium first, right? It is because the proof is like this, right? Suppose all the other firm, okay, have price higher than C. Okay, suppose equilibrium price is not C. Okay, it cannot be low, because below you're losing money. People would not doing it, right? If higher than the marginal cost C, then you undercut, right? Because you set the price between the market price and the C, you get the whole market, right? Then it can't be equilibrium. So the only equilibrium possible is price equal marginal cost, right? And the problem, I mean, you look at the IO textbook, the T-row textbook, they spend actually a whole chapter to explain why. Because the literature actually call it Bertrand paradox. Because economists don't understand why, right? Because it's just a price that's usually would think, right? It's homogeneous market is often common, and why you see this happen, right? And they can never understand that happen. Of course, if you look at what happened now in the mainland China, the offline store for the restaurant, then it's almost zero profit. Everyone's losing money anyway. I mean, or they're breaking even, right? The price equal to marginal cost, right? Or the online store is actually there's not many profits making, right? It's Bertrand competition, right? It's homogeneous good, right? So, and there are many explanations to what is the missing in the model. Okay, there's one thing that actually problem mentioned missing is, I think is the most practical one, is this assumption, the demand function where the price is less than this. Okay, you can supply the whole market. Okay, look at the restaurant. Suppose I set my price to zero, even. Okay, can I serve the whole market? Can I serve the whole China? Can I serve the whole Hong Kong? Can I serve the whole Satin? Even, right? Even in here, even the canteen here, if I set the price to zero, I mean, I'm the lowest price. Not everyone in the school to come, right? Even everyone in school to come, I cannot serve everyone, right? They're what we call the capitalist constraint. So I can really produce the whole market, right? There's some constraint that I can serve. And that means that, I mean, even though I set the price as low as zero or marginal cost, right? I can't have the whole market. Or even I want to have, I can't actually serve. There's a constraint to do that. That's why the price is above the marginal cost. And okay, so that would be one reason. Okay. And second, of course, they would say goods are not homogeneous, right? That is one way. And of course, some paper, actually famous paper, that reword the idea, because firms know that when goods are homogeneous, they will end up in Bertrand. That's why firm would differentiate. Okay. And by differentiate, they avoid Bertrand. Right? I mean, how to avoid differentiate? That's famous hoteling model you learn in the principal class, which we can cover later in the game theory, right? So we will try to differentiate with different color, different shape, different style, make sure that they are not the same, right? So by differentiating, avoid this Bertrand paradox. So you can use this problem in this result in two sense, right? Either you add more feature to the model so that this result will not be true, right? Or this is a baseline model to explain why you have vertical differentiation, horizontal differentiation, a lot of feature that's not incorporated can be done there, right? The firm decision. So you can see, I mean, even this kind of simple model, you can do a lot of various stuff. Okay. And in many applied model, actually, they would have assume Bertrand is fine. They do in assume Bertrand to make the model more simple, right? They may consider, okay, there's a suppose supply chain model. They want to make, say, the supply is very competitive, right? Maybe the consumer side is not so competitive, right? But the raw material is very competitive. The raw material become Bertrand, right? In that case, when you have Bertrand upstream market, then you don't need to model it, right? Because the marginal cost is determined by the input price and the model much simpler. So by assuming Bertrand in certain states of market, certain segment of market, your life is easier. Actually, we have done that when looking about the firm production. We assume the labor market or the raw material is perfect competitive. We just buy as many as we want at the same price, right? So actually, we often the time we invoke this kind of stuff all the time. Okay, so even Bertrand by itself is something we think is crazy. If this is our main model, but it can be part of the side model. Some market is assume Bertrand, then you're done. Okay, some part may be monopoly, then you're done. So that's why you can combine stuff, right? Maybe you can think the upstream is Bertrand, the downstream is Carnot, right? Or the upstream is Bertrand, downstream is monopoly, upstream is Carnot, downstream is monopoly. You can mix and match, right? So that would be there's a lot of things you can do, right? Or you can have perfect combination in the upstream, Bertrand downstream, and so on and so forth. And there are many things you can work on, right? Or you can think about market segmented, right? In the market for the normal, the inferior good is perfect combination. The inferior is Carnot, is also fine, right? That's what happened in Hong Kong restaurant, right? The two lang song fan, so two dish, right? Then it's like you can assume Bertrand, right? And restaurant assume Carnot, right? So these are the things that you can actually consider in your model you want to build, right? And there may be spillover between consumer, right? You can make the demand function a little bit more funny, but here, then you can do a lot of stuff. Okay. Now the next is look at another model, which often used in trade model or IO model, is to assume heterogeneous product. Okay. There are many ways to produce heterogeneous product. We talk about this model is just a standard downward sloping demand, okay? And you can have the Hotelling model, which I don't have time to cover right now. Maybe we can talk about game theory. Hotelling model, Charlotte model is the circular model, or there are many type of model you can incorporate there. You can look at the handbook of IO. They have a lot of thousands of models to talk about this kind of stuff. You can invent your own thing, okay? But right, I mean, if you look at the if you're from real estate department, right? Then the famous hedonic model, right? There's a lot of those stuff can be done there. There's a feature there. But anyway, so let's assume every firm faces a downward sloping demand. Okay. Now, do you know that each firm has its own demand? Okay. QJ. Okay. And the price is different because different good. The cost will be based on the same cost function can be different, but for simplicity, they make the same, but they can be different. And this is the profit function, right? Revenue minus cost. Okay, nothing new here. Okay. And if we assume this short run with no firm enter exit, we can have standard Carnot-Nash equilibrium. Every firm is choosing the price or quantity, doesn't really matter anyway, the same thing because downward sloping demand, right? And choose the price here, right? Such that this maximize. And you can see in this case that it actually is very similar to monopoly, as I mentioned, right? The FOC will be same as the marginal revenue, marginal cost, right? You produce more, then you increase this marginal cost, right-hand side, right? And this marginal revenue, you produce one more unit, you get increase the price, right? So you increase the price more, then this means that you said this is the revenue of what you have been sowing, you sold this much, right? You increase $1 to the product, right? Then currently what you sold will get one more unit of money. So that's QJ. And this part will be because you increase the price, you actually sell less. There's a reduction in the demand, right? Time existing price. So that is the loss in revenue due to increase in price. This is increase in revenue, assuming the same quantity being sold. The difference, right? The net effect will be the change in revenue. This is you increase in price. This is the say reduction in the quantity you sold, right? Then if you reduce the quantity you sold, then your marginal cost, the cost will just go down, right? So this is the marginal cost, and you will equalize. right? But you do know that that will be MI or MC, right? And you may ask, what's the difference between here and before? Okay, why we still have MI MC, but why is it the same as monopoly? The only difference lies on this one, right? This is the same. The only thing is the MR is this guy, this P, Y, or the Q guy. The reason is being that our Q not based on own price, but a bunch of prices. Right? Before monopoly, just only your own price. Now the P is a list of price. So that's why you remember the net is based on other people prices. Right? So before this price is fixed, right? But now this value depends on other people prices. And this Q also depends on other people prices. And this also depends. So everything depends on other people. Right? Because depend on how other people set the prices, affecting the quantity. Everything is related. Right? So there's a J system of equations, not necessarily linear, but potentially there can be more than one equilibrium. Right? So, but that would be the idea. Okay? And if you impose the condition of no entry, that means zero entry, means free entry condition, right? So zero profit, then they will be equal, right? But you can easily solve this problem, okay? If I give you the explicit form, right? I give you the price, quantity, you can solve it without any issue, okay? But this is the one way to look at the model easily, right? Because if you don't worry about the specific nature of competition, right? You can write this and then you're done, right? Because it can be Carnot, can be Bertrand, right? Because here I choose P here, you can choose Q, right? The same thing, right? Of course, there's some difference here and there, depends on the style, but that would be the model. Okay. But we'll give a assignment, then probably you have work a little bit, and then you will see difference here. Okay. Is there any question? I mean, I think I'm fast because this monopoly, Bertrand or Carnot, you learn in the undergrad. But I just now what we learn is try to properly put the formula here to do calculation. Then we look at the general equilibrium, if there's no question. So the idea of general equilibrium here is not to tell you how to prove certain existence of equilibrium, which very few people actually doing it, but rather we're trying to introduce some concept of what we call productive efficiency, core individual rationality, which is still used in contract theory, used in a lot of experiment, used in a lot of context. This part is sometimes referred to cooperative game theory, 合作博弈. So that's different from the non-cooperative game theory that we will introduce the second half of the course. Okay, and for those who still use it, asset pricing people still use it. You will see the textbook, they would still working on those problems. And of course, the main two results that we will try to show you or claim is the first welfare theorem or second welfare theorem, which said competitive equilibrium has nice property of Pareto efficient. And second welfare theorem would say any Pareto efficient outcome can be implemented as a Lavoisian equilibrium. So the market outcome is good. So as long as you allow you to do right thing, okay? But let's see. So will be notational heavy, so I go slowly. for this one because not that easy to consume all at once. So assume that of set of consumer 1 up to I, okay, and consumption of good K on consumer I will be X sub I sub K. It's a little bit tedious, okay. And consumption bundle for consumer I will be both I and X1 up to Xn. So the n different goods, okay. And so it's different from the chapter 1 where we have n good for one consumer, but because now we're multiple consumers, so that's why the superscript is the individual. Again, the subscript is the good. So there's a consistent notation here. And here we assume the preference can be represented by utility. Okay, then you know what is needed, right? As long as the preference is continuous, okay, or if you want monotone, but need not be, but continuous monotone it exists, right? If not continuous, like lexicographic, it doesn't. But as long as continuous, this is fine. Okay. Now here we're different from the chapter 1. Is we will start with endowment. Okay, instead of income, one thing income, we'll start with everyone start with goods. Okay, they will have a vector of commodity that start to begin with. Okay, you may ask, okay, why? I mean, I never endow with anything, right? Did I endow with apple or banana or French fries? No, I never endow with that, right? Well, you may ask, but we can earn income, right? But no one actually endow son, no one endow me with money, right? So why they would do that? Okay. So this is how they model without production. That's what I said, right? Because in reality, people want to do production, right? We learned chapter 2, right? There's a firm there doing production. But in this model, we don't want to talk about production. We don't talk about firm at all. Just people trade, okay? And you can imagine that some of the farmers, so they may be good one is apple, it's apple tree. So he may 10 apple, other thing is 0. It's allowed, right? If I'm a one without anything, right? Maybe the last one is surface, okay, teaching, right, or do research. I have 0 of everything, but I can do research, I can teach, right? The time I have, I can exchange others, exchange other goods, right? So no one enjoy my time, but maybe some people need my teaching, right? As like you, right? You have to take my course to get credit, right? So that will be the idea, okay? So it's still okay. It's not too crazy, right? The production is in the background, but we don't allow production here because the production will make things a little bit more complicated. And that's a way of technique of building model, right? Unless you really model something, otherwise you just assume that it's gone, then make our life easier. Focus on what's the main focus, because you can't model everything, right? So that's okay to ignore things we don't care at the moment. So that's why in classical model, that's called exchange economy. So there's no production. So people are given some good from the heaven, and then they just exchange. And we're going to see this exchange economy. If now people trade, is it going to be okay? Okay. So that's why you can assume this is a refugee camp. Red Cross come in and give everyone something. Okay, you can exchange. Or prison economy, right? In the prison, you just have something given to you and then just change. Okay, so there's no production there. Okay, the economy is represented by very simple preference and endowment, or you can start with utility, the same thing, right? Because preference represented by utility function. Now the economy, this is set up. What's the outcome of this economy? Will be this allocation, right? You always have a current problem. We start the problem, and then what's the solution there, right? Allocation is kind of any solution to this economy, right? The economy solution will be just I consumer, what they consume, right? Each one will consume n different objects. So that's why n times L, right? Guy number 1 will consume n good, right? Guy number 2 n good, n times L, right? So that will be allocation, right? So this is the problem, this is the solution or the outcome, right? So you can change this one, get it more complicated, and solution can be more complicated, right? There's all economic problems like right in this way, right? Same as what we do is like we have been doing that, right? So this setup, this is solution. Okay. And the first thing is feasibility. You have to write down this way, standard way to write the problem in this way. So to tell what kind of outcome is feasible, right? Feasible means that no one consume more we have, right? So adding every consumer's consumption on good K should be less than or equal to what they have on in commodity K in aggregate, right? So if you write in this form, or you can write compactly in vector form, right? By vector form means for every element, the standard notation, right? You compare vector, you do coordinate-wise, compare element 1, element 2. So element 1 in the first vector to element 1 in the first vector, element 2, same thing. So this is standard notation in compare vector. Okay. It's element-wise inequality. Okay. And we define this as a set of feasible allocation. Okay. This is a little bit abstract, but actually you learn it in SWOT box. Do I have that? I don't have that. Let me write that down. You learn in undergrad, right? Usually when you learn the general equilibrium, you will learn it in like this, right? You write, right? This agent 1 and this agent 2, right? And this will be what? This will be, okay? You can represent the endowment like some point here, okay? This is E11 plus E21, okay? And this point, this here is E11, right? And here, look at this from this direction, your eye is here, right? This is E21, okay? And the height, right, will be E2, let's see, E12. Okay. This height will be E22, right? So the horizontal direction is good one, right? It's good one dimension, right? This you learn is good one, right? And this is good two. Okay. The length of this is the size of how much you have in aggregate, right? And this is how much you have, right? So if you fully allocate, you don't waste anything, then any point in this box is a feasible allocation, right? Outside the box is not. Of course, this is not complete description because I don't allow you to throw away stuff, right? If I allow to throw away stuff, that would be not the point in the diagram. Instead, you have 2 points, right? Is that okay? Okay, so that would be the feasible allocation would be like this one, because it's okay to restrict to this one, because later you will see when you assume utility of monotone, then you always go to this one, right? You always have this SWOT box. Those are SWOT box is the feasible allocation. Okay. Now go back to the question here. Okay. Now, as we said, I mean, we later will assume continuous, right? Because monotone and strictly quasi-concave. Why? Because that would be one unit solution to make our life simple, right? Strictly quasi-concave is a unit. There's a demand curve exists. right? Marshallian demand exists. It's not correspondent. This is a demand curve there, a demand function there. And of course, you may complain, but this is what we do. Consumer will take price as given. Okay, so this is same as what we learned in the beginning, right? Maximum utility subject to budget constraint. But the only different part is here is your income depend on the price. Okay, why? Because you have Apple, right? Your income is start with the good, right? How much income you can do depend on how much your Apple can be sold. Okay, so that's why with the general equilibrium, we say every prices are determining equilibrium, right? Because we don't want to leave anything unturned, right? The only thing you set up in the model is preference and endowment, right? And at the end, you get the allocation and the prices, right? Because we want to talk about market prices. The prices is generated in the system, right? Allocation as well, right? The market will give us the allocation associated with the price, okay? And consumer under the market will take the price as given, okay? And this price is endogenous, okay? So the income depend on the market, so it's not given, okay? But for each individual, because price taker, right? So this is the constant. Y, you can write Y, right? So still, this is the same problem. That's what we learned in topic 1. Okay. So the unit solution is continuous. So that's why that we have proof already. So we don't have to worry, right? Just to remind you why this is unit, because of strictly cosine-concave. Why it's continuous? Because continuous. Actually, the proof is there. So we don't need to go continue there. So what is left here is very important term that we will do the proof, okay? Is we call excess demand, okay? Let's define it and then we will explain why it is important, okay? Excess demand is called Z, okay? Z is it's a bunch of each for each good, so n good, so the n numbers. Number K1 represents K good excess demand. Excess demand means this is Marshallian demand. How much at this current price, how many good I would want, okay, the sum of the demand minus how much people would have, okay? And we would say the market is good, okay, as long as the excess demand is 0 or negative, right? As long as we have enough to cover, the market system works, right? The only problem of resource allocation is we have insufficient, right? There's no problem with more than what we have, right? Right? So the problem is how can we solve this problem, right? As long as the excess demand is negative or 0, our solution is nice. We can solve the problem. Okay. So we want to have the price such that this is 0 or negative. Okay. And here we will prove certain property here. First, okay, continuity, because this is continuous in P, so this is continuous P. So that's a proof. Second, homogeneity. If you double the prices, you actually will have no change in the X, so there's no change in Z, right? Because double the prices, you also double everyone's endowment, right? So there's no change because this X is solved by this guy. You change everything here, there's no change, right? And last one is a little slightly more complicated by Watt's law, which I'm not going to prove it, but it will say the value of excess demand is 0. But what we want is this is 0 for the system to work. We want the price as it is 0, but at least it can be shown the price is 0. The proof is here, but I'm not going to prove it. Just involve manipulating inequality here. The idea is everyone will use up his all budget. Okay, and at the end of the day, it must be 0. Maybe I can go over the proof quickly because it will be fun to look at the proof. Okay, first one I said is simple. The last one maybe I prove a little bit because it may be fun to look at. Okay, so we would know the Wawa's law say what? Wawa's law we have remember in the topic 1 say if preference are monotone, budget will be binding. Everyone will consume everything. There's no leftover. If you forget, let's go back to here. So we said the following, but the proof is very simple, right? Because if it's good to you, it's monotone, budget is binding. You use up all your money, right? So no, because everything is good to you, right? So you don't want to leave the money on the table, right? But anyway, let's do this quick proof. I mean, the proof is not important, it's black, but I want to show you how this type of proof being done. Okay. So that's why first is budget binding, which means that every individual I look at his budget constraint is binding. Okay? Because budget constraint is this one, right? Budget constraint is this guy. Right? So it just must be binding. Then you can add up all the individual from 1 up to L. So this is budget constraint. Add up everyone, still 0, right? Everyone 0, add up everyone 0. Is that okay? This is no one leave money on the table. So everyone add together and aggregate no one leave money on the table. Fair? Now the key part is here. That is the trick part. Reverse this summation. Okay, that is the trick part. Ask me why, how the trick, but there's a trick. There's nothing new. The summation is order. Is that okay? Just swap. You can always do it, right? Because depend on how you add things, right? You add the row first and add the column, and the column is the same thing, right? Doesn't really matter how you add, right? Addition is commutative, right? It's no matter how you add the same thing. Now the key is like this one. That is the little bit why we do that, because once I swap, this depends on K, I can take the K out, right? And this defined to be excess demand, right? Because this is good case demand, right? By I, this is add up together, this is excess demand. And then we go back to here. How we define that? This guy. Add up everyone's demand on good I, good K, minus the sum collection of the what we have, right? So good K, how many add up all people's demand? Good K, add up every people what they have. This is excess demand. This is 0. So the value of excess demand is 0. So P dot Z is 0. So it's very simple, right? As long as people consume everything, the value of this excess demand is 0. Okay. So I mean, the proof is nothing but to show you that the trick is reversing summation. Often use trick in this kind of equilibrium proof, and okay, and it's not unusual. This is very common. You will see in the main proof. Okay, that's why I say the Wawa's law. And you may ask, okay, why we care about this? Okay, and this immediate thing that is saying that may or may not be important to you, but you will say when there's an N-1 market, they're clear, the last one will clear. Okay, because if everything is 0, the last one will be 0. Okay, so I mean, of course, it's not very important, but that is what he said. Okay. So now I think that will be something important. We're trying to do something interesting. Is the following. We want to show the market system works, right? At least one thing we need to show is there's a price such that this excess demand is not positive, right? Because no one want more, that is a good thing, right? If someone want more at this price, then people are not happy, right? That is what people complain about the system, right? I want to buy more, but I can't, right? But I want to have something, okay? So here is the main statement, okay? And in fact, this is people's in this literature, they spend the whole time to prove this kind of proposition is under different condition, this thing exists. Of course, you can add a bunch of stuff there, but they will spend more than, I think, at least more than 100 papers try to prove this kind of result. There exists a price, excess demand is zero negative. Of course, they would do a very general condition and all bunch of stuff, but that is what they do for a living. I mean, there are a lot of people basically proving existence, okay, under various conditions. Maybe they're public good, maybe they're firm, they're increasing return, there's a club good. I mean, a lot of externality there, they still exist or not, okay? Because in the world we have, right, there's a lot of stuff, right, that doesn't satisfy this condition. So they try to enlarge this to see if there's a firm there, the firm of market power, there's a lot of features, this still solve the problem. Of course, this type of research actually was very popular in the 80s. And that's, you see the MWG, the book, right? There's you see huge literature on that. But especially in the 70s, 80s, especially the Lemons market, which we will mention next class as well, is information asymmetry. A contract theory comes in, and this become less important because if you remember the Lemons market, right? Basically, market destroy, right? So why talk about market at all? Because market doesn't exist anymore in its standard sense. So we need the market design, right? When market fails, we need engineer, right? We need to design a platform. That's why the information system people make money, right? That's why we have monopoly, right? And how to regulate monopoly, those kind of issues here, right? But in generic sense, in many cases, this still applies. So that's why we still learning. And in financial market, this thing would apply as well because market is competitive enough, everyone's small enough, this thing would still hold, right? That's why in finance asset pricing, still the current model, I mean, look at the textbook, they still use general equilibrium setting. Of course, in KVM model, probably you may know, we just assume everyone has the same preference, the KVM model, but you have many things as well, but that would be the idea, right? So just like is such price whether exists is a big problem there, right? It's the price that solves the model. Not even mention about uniqueness, not mention about what property what we have. First, we worry about exists or not. Okay. So that is also what you do is you have a new system. You want to make sure that everything works nice, you have to prove existence. Okay. And the proof is super crazy. Okay. Not going to go to detail, but let's finish. You have make some assumption here and construct a function that have a fixed point that they will use the Bauer fixed point theorem to prove it. This is the classical technique when you talk about the standard, the first generation of general equilibrium approach. When you go to second generation general equilibrium approach, this technique is not sufficient. Okay, you have required the manual for more complicated differential geometry to prove stuff. So basically, this field becomes so mathematics. So I'm not sure that anyone would, if you're not math oriented, would be interested in doing this research. So even this technique, very complicated itself, is not many one use it anyway. So I'm not going to talk about this because this is more or less obsolete. Okay, because the new one, they require differential geometry, those kind of things. I mean, only math major would able to handle. I mean, I'm not going to bother you with all the math, but you can see that we have a very clever construction of equilibrium function and prove the existence of equilibrium like this. Okay, and I'm not going to talk about that because I don't see anyone would be using this. Okay, for the record, actually, my advisor actually do this. Okay, and yeah, so I cannot say anything bad about it, right? Because it's still very interesting. But it's very difficult to make for a living if you want to research on this. It's very hard. Okay, so and then you can see, right? There's 1 page of proof, 2 page, and then continue to prove it. The fixed point theorem. Okay, and then you go again, 5 pages of proof. Okay, then I'm not sure anyone would be interested in this. We're bored to death if I go over every single line. But I think I written the slide in a case that even you read it by yourself carefully, you can understand the proof. Of course, you can always check back the textbook. Okay, so let me have this last slide with a break. Okay, this last slide. Go. Assume we done all the math. Okay, just believe us. I mean, we have that. I mean, even though you don't believe me, look at the textbook, right? So always exists under our assumption. Okay, then there will be a Lavoisian allocation, right? Because at the end, the price allow us to achieve the allocation, right? The allocation is our goal. Price or the market that led to the price is just the mechanism of the tools, right? So we will say a Lavoisian competitive market equilibrium, whatever you like, as long as the price vector allocation such that everyone's at a budget constraint, everyone's maximize his utility given the price. Okay, this will exist. And after the break, we look at what the property of this equilibrium. We look at first welfare theorem, second welfare theorem, and some core property. Okay, so that would be the goal of remaining 19 slide. Let's have a break of 15 minutes and ask me any question during the break. I see you 15 minutes later. So I don't know, do we have class next week? Is it September, October 1st? So, oh, so then we have holiday. I don't know, fortunate, unfortunate, but fortunate, yeah. But I hope we don't need to make up. But if we do, then let's see what happens. Let's see how to do it. But as same as last year, if we do make up, then the makeup will be optional. I cover something is optional. So I cover the main thing in the main part, and then we do just probably, I mean, in the exam, we just limit to the 8 topics we have, and we make up them will be not part of the. So I mean, some of you actually told me that this is a little bit more complicated. I just want, I mean, a little bit fast because most of the thing actually you don't really need in your research. Okay, but I still want to do it. I mean, of course, you have to know some of the result. I mean, not the how to prove it, but also I want you to show you that how this type of problem can be done, right? What this type of problem is, like you start with a problem, mathematical model, right? That is how we do is like, it's similar to the consumer, right? Start with some setup, right? Consumer problem or firm's problem. Start some setup with some assumption here, and we have some outcome or solution we want, right? And then we impose what condition we want to have, right? First is we want allocation to be feasible. Second, we want that the outcome, right, under the price system, the excess demand is non-positive, right? And then we will decide this equilibrium. So this is somewhat water standard, and actually is very common you see in finance and accounting literature, right? In a lot of the model, it's very difficult to solve the backward induction kind of or game theory style model equilibrium. So what they do, actually very often in 80s in the model papers, is they have a structured economy or some agents and some resources, and they declare an equilibrium will satisfy certain condition like this, or in this case, I have maximization of budget constraint, right? Or you can just make the model such, okay, this equilibrium, certain condition is satisfied. Say maybe demand to supply, or no one more than what they want, and so on and so forth. And you can solve the equilibrium. It need not be a Nash equilibrium. It need not be any equilibrium in game theory. It need not be any thing related to that. As long as you define certain equilibrium, or you can solve it. And sometimes, because why you have to do it, because the standard equilibrium is very difficult to solve. You may limit yourself to certain type of equilibrium, maybe linear equilibrium, or a certain type of equilibrium such that this thing would hold. Okay, so that is we will do. Okay, later we focus on the core, those kind of solution concept as well. Okay, but this is a equilibrium concept here. Okay, now we are going to look at other solution concept besides Watson equilibrium. We look at the concept what we call Pareto efficient allocations. Okay, Pareto efficient is actually means that you can't improve everyone strictly. Okay, there's no way you can improve without harming others. Okay, that is Pareto efficient, right? Because it's the weakest efficiency concept, right? If you have to improve someone at the expense of other, then I don't know how to trade off. You need to tell me trade off. But if you can everyone unanimously improve, there's a good thing we should do, right? Pareto efficient is there's no way to improve everyone. Okay? If I have to improve someone have to be worse off, then it is Pareto efficient. Okay, and let's go back to here. Maybe go back to this edge work box. Suppose without with this endowment. Okay, Pareto efficient means that, okay, whatever allocation, okay, maybe at this, I don't know, this is the point, maybe this is the point I have. Okay, Pareto efficient means that, okay, you can't choose another one such that both are happy. Okay, so to make in perspective, let's draw some indifference curve. That's what you do undergrad, right? Suppose this guy number one indifference curve like this, passing through here. All right, and this is everything is better for agent one, right? So agent one will be happy if go to anything in the blue area. Okay, say. And for number two guy, his indifference curve can be anything but, say, suppose this is the one. Okay, that means that this area is good, right? So this is not Pareto efficient. Why? Because this purple area is the area that when you reallocate anything in the pink area, is better for both. Okay. That means that if you try to look at this two-person algebra box, only if they're tangents to each other is Pareto efficient. If they're not tangent to each other, the difference curve passing through that point is not tangent to each other, then you can find some way to improve, right? Well, by tangent means if you remember the other red one, suppose it's like this, right? Then the beta set is like here, there's no way to improve, right? So only if there's no intersection, right? You draw the indifference curve, and there's no intersecting area for the beta set, then that's Pareto efficient, right? That is how, that's all the Pareto efficient outcome. So let me repeat what Pareto efficient means. There's no way, no other location you can find them such that you improve two of them, in two people case, two of them all together without worsening the others, right? In this case, okay, the deep red one, right? You can go anywhere, okay? You can, if you go this way, you improve one, right? You go this way, you improve two, right? If you go this way, actually you're worse off, right? So there's no way you can improve both. Look at the deep red one, right? You suppose deep red one is the case, right? There's no way to improve. Go this way, improve one and harm two. Go this way, improve two, harm one. Other way around, you harm one or two, which is stupid, right? But there's only the best thing, right? So that is called the Pareto efficient. Okay, Pareto efficient is, there's no way that is improving. Okay, so this efficiency is often used in many contexts. It's a base idea. So look at all the system. If you want your system to allocate resources to be meaningful, it should be Pareto efficient, right? Because unless you have some reason why there's mutual gain you don't exploit, it's very difficult, right? Just like you left some money on the table, okay? And indeed, you do experiment or you do some reason. Actually, there's some reason you want to leave money on the table, okay? But in general, it's not. When the complete information, everything is nice, there's no way to left money on the table, okay? But there's some time you left money on the table, but in this model, it's not the case, okay? You should not leave something unallocated, or there's something you can improve, you should allow that to happen, okay? So actually, there's one of the first things that actually the economists would say why market is good is because the velocity equilibrium is Pareto efficient, right? So look at the proof is, read the proof, but the idea is very simple, okay? Is look at the price, right? If the price is in equilibrium, no people want to trade further, right? If there's a gain, you can trade, okay? And the price are such that, okay, they're tangent to each other, right? It's just like, right? One way to think, the proof is like this, actually same as your undergrad proof. Okay, let me erase this red color. Okay. So this is the case where it's Pareto efficient, right? And if you have the price like this, right? This is the price, then done, right? Because no one can trade in the price in this way. At this point, no one can trade. As long as the price is in between these two beta set, right? And this is the where you can't really, no one can really do anything, right? So that would be somewhat along that line. This is a proof. Okay. The proof is just like 4 pages of the proof, but I don't want to ruin your afternoon by actually proving the thing. But I can sketch the idea. The idea is very simple. The idea is like the following. If there is something that can improve, actually evaluate your budget constraint. So that is the idea. You prove the idea is like if the allocation that improve everyone, okay, and within the budget constraint, then you cannot, it can't be Gaussian equilibrium. So it will, when you calculate everything, the next slide, it will say, okay, this more than your budget, and there's a contradiction. So I'm not going to follow the proof because we don't have time to go over the proof, and I'm not asking you to prove it anyway. Okay. Okay. But the idea is like this. Okay, let me at least draw a picture to show you how the proof is being done. So the idea is like this. Okay, start with actual box. Okay. Start with some endowment point. Okay. And right, in this case, right, at this point, you can draw some indifference curve. Maybe I use blue. Maybe I should use the right color, right? Otherwise. So you can draw indifference curve here, right? So this area is better for guy number one, right? And you can draw indifference curve for guy number two here, right? This is the beta set, right? And okay, so the idea would be like, okay, how can we make sure that this is the case, there's such a price will exist, there's everything all right? So one of the thing is, you think about the set of Pareto efficient outcome. The set of Pareto efficient outcome is, this is Pareto efficient, right? Everything give to guy number two is Pareto efficient, right? Because you cannot make one happy without harming number two because everything, right? Same, this point is also Pareto efficient, right? You give every number one, then it's also efficient, right? Then actually, because of the shape of the cosine concave, you can have a line which is set of Pareto efficient. Usually it's a line, something like this. I don't know how you get it there, but anyway, somewhere here, right? It's a set of Pareto efficient outcome. Can be thick, can be thin, but anyway, just make it, in our case, it's just a line, all right? And you can have that, then how can you construct, right? It will be something like this, right? The price is here. I don't know where it ends, but as long as you draw the price, any price here, right? maybe somewhere here at this particular point, okay? And happen to be, you can figure out that it must be the case that the indifference curve is here, is in tangent, right? Because it's partially efficient, right? And the blue one is like here, okay? And in this point, it's partially efficient, right? And so the price is here. This is fine. All right, so that is why it satisfies welfare theorem, right? Because okay, horizontal line here, right? And if not, then you will figure out certain way to improve. So that is why graphically it would work. Okay. And this is the first welfare theorem. Second welfare theorem actually follow the same idea, very similar. Okay. Let me show you the second welfare theorem and then come back to this graph because the proof is not too terrible. The proof is again a little slightly similar. Okay. Is that every productive efficient allocation every productive efficient allocation can be implemented by a market. Okay, so that means that if you care about only care about productive efficiency, the market can get it for you. Okay, with some suitable redistribution of income, you can move around your endowment. You can do lump sum tax, okay, which we know is impossible, but suppose it's possible to do it, and that means that we can always do it with the market. So market has no problem as long as your taxation system is efficient. Okay, that is more or less what it said. Okay. So basically, the proof is very simple, but I'm not going to do the proof, but the idea is like this. Suppose this is your endowment point is E here. Okay. What you want is not this point, right? This is the set of productive efficient outcome. You want to achieve this particular point. This is your social ideal point according to everybody that, for example, this point is nice. This point is nice. Okay. What about this point? This is our ideal point. How can we achieve that? Okay. And at this point, you have an indifference curve here, right? For player 2, you have indifference curve here for player 1. Sorry, the individual one, right? Because this is how the indifference productive efficient here, right? So you have the tangency here, right? The line here. Okay. So there's a flat line is the tangency to this point. Okay. So suppose a perfect taxation system, you move this point somehow to here, whatever from the flat line. Okay, the market will bring you to the green one. So that would be the idea. Okay, start from here. You can go to whatever black, you can go to the green. That is the proof. Okay, so I'm not going to talk about the proof, but that is the meaning of the second welfare theorem. Means anything there can be implemented by taxation. Okay, because you can tax, move around. Okay, but of course, looks like crazy because if I know, then why I just don't tax this? Why I just cannot tax to this one, right? Why it's so complicated? Okay, move here and move there. I don't know, right? It's a philosophy problem, right? If I know this point, right? Why I just don't tax to here? But they don't talk about that. But they just say, okay, it's possible. You can move around this. At the end, go to here. Okay, but that's a proof. Okay. The proof is rather not so complicated. Okay. And possibly I want to remind you the one big thing is this Cauchy concavity is addition compared to first welfare theorem. First welfare theorem actually don't require Cauchy concavity, but the second welfare theorem do require that to happen. But usually that is usually what we want to do, right, is saying the market going to deliver efficiency, productive efficiency, and any productive efficiency can be implemented by market. So that is usually this we want to have the duality here, right? So that's to demonstrate the system is good, right? So so there's basically to say there's something the market can do is good, and market can do most of the thing you want. So that is the proof here. I don't want to go into detail because I want to draw your attention on this kind of property game solution, which I think is more important when you learn contract theory, when you learn system design. This is something that used more often. Okay? And of course, you can, as I said, right, there's a lot of people working on general equilibrium, right? And people are not fully satisfied with productive efficiency, or simply, or that will be sufficient, right? Because productive efficiency is a very weak requirement, right? Requiring that everyone add on together, right? Productive efficiency means that things that everyone can benefit, we should do, right? So we kill off something that's not benefit everyone, right? But they allow too many things to be there still. Okay. So we will allow a stronger condition. Okay. First thing we have to introduce is what we call individual rationality. Okay. Or sometimes they call the endowment lower bound, which means that you don't have to be in the market, right? So you can consume what you have. So that means that no matter what the market gives you, should be at least as good as what you have initially, right? So because you can run away from the system, right? In the old days, right? I mean, when the politics are bad, people run to the forest, right? 竹林七贤, right? Those kind of people, 隐士, so people just hide, right? Right? So which means, for example, like this, right? You get married, you get this one, right? Getting married must be better than you become a single, become a bachelor, right? Not the bachelor you have, right? But you want to be bachelor, right? You want to get married because marriage give you more than become single. Otherwise, you don't get married, right? Otherwise, unless you're crazy, you want to be tortured. Otherwise, getting married should be getting higher benefit than become single. Otherwise, you divorce, right? So that would be individual rational. Okay. With that being said, don't laugh because there are a lot of papers these days talking about we should ignore this constraint because you're not allowed to opt out, right? So you don't have to worry about the IR constraint. Okay, but that would be another. I mean, no laugh. I mean, this is real research. Right? People actually talk about you can't opt out, so that's you don't have to respect this kind of IR constraint. But anyway, the second one is actually related to what we call property game theory. Okay. So probably you what distinguishes the property game and non-property game theory? Okay. What we learned in the second half of our class is non-property game theory, which saying that we would define how people behave in detail and define what equilibrium. Actually, you see, right? In the firms, we decide quantity or prices, right? Bertrand column model, such that if I don't deviate, the other don't deviate, right? I will give detailed instruction how people choose their strategy. That's called non-cooperative game theory. Okay, we would decide what they can be done and what with the equilibrium concept. Okay, but here we would do is instead of doing this cooperative game theory is asking what should be the outcome that is stable directly. Don't mention about how to achieve it in the micro level. What is this nice solution? We don't want to talk about whether firm behave. We don't talk about whether firm choose quantity or price. we talk about the outcome. Okay, was a price or quantity that actually is a nice one. Okay, we don't talk about that. Okay, so here in this context, we focus on the following. Okay, look at the outcome directly. Allocation. Okay, don't know there's no price at all. Remember, we don't have price. Why we don't do this? Because economists want to study the case where price is not there. Any system can be done, right? Maybe communist system, maybe mixed system, okay? Maybe dictator system, okay? Maybe some crazy AI system, whatever is included. Okay, there's nothing bans you from that, but because we focus on the outcome only. Okay, how to achieve this outcome, we don't know. We just say what outcome are good, what outcome are not okay. Okay, so what we do is we say an outcome that is blocked, so we take it out from there. Okay, remember what we do is we start with the outcome, what possible outcome. We have some property, take what our outcome is not feasible. What is left is our solution. Okay, without telling us why this outcome is not good. Okay, so we say some outcome is blocked by some group of agent if exists other allocation such that if they want to use up their own resources, they can be better off. Basically, it's just like with a system. Okay, I say this allocation is not good, it's not feasible, should not be equilibrium, should not be part of the solution. If some of the people, they break away from the system, they go to an island, do what they want. If they do what they want is better, then this is blocked by those people. Okay, and IR means they block by themselves, one man blocking. And blocking by coalition means a group of people. It's more general concept. Okay, because the first one is blocked by the guy exit the system, and this blocking is blocked by group of agents. Okay, so that comes with the first cooperative game concept called core. Okay, core means that an allocation that's not blocked by any subset of agents. Means that I have an allocation. You can't take any group of agents that they take the endowment away and better off. Okay, I don't talk about how they achieve it, but just saying that it's possible for them to do it, then they can do it. Okay, there's no system to achieve this. Okay, it's not talking about after they go, are they going to be stable? Okay, no, talking about that. Cool. Okay. So that means that something is a core, means that there's no way, okay, no feasible, no other allocation, such that these people, we allocate what they have. Everyone is weakly better off. Some of them is slightly better off. Okay, there's no way to improve it for some of them using their own resources. Okay, this is, you can imagine this is a system itself, internal stability, right? And the allocation, you can't think of, okay, let's forget about the system. We do it on ourselves. We don't specify what system you do, but we do something. Okay, this is the core. Is that okay? So the first proof is very simple. Core are individual because IR is just one man blocking. So core is a more general concept, right? Allow any arbitrary thing. And core are all productive efficient because productive efficient means everyone together a block, right? So that means that if you want to be like this, so all feasible allocation will be F of E. Okay. And you can draw a smaller one, right? This is individual rational. Okay. And there is something Pareto efficient is here. Okay. And core is here. Okay. So that when all feasible, individual rational is here. Right. Pareto efficient is somewhere here. Okay. So why we want to care about this kind of game concept? The history is like they are useful in many contexts, but one of them is saying that, okay, we don't really rely on price, right? There are many things can be done, okay? We want to see if actually Lavoisier equilibrium is part of the core. The core can be very big, right? Turn out to be yes. Lavoisier equilibrium turn out to be part of the core. So basically, what we expect is this. It's like the first welfare theorem. We figure out that the Lavoisier equilibrium is actually here. Right? This is the more like first welfare theorem, right? It's like Lavoisier equilibrium is Pareto efficient, right? But it's stronger. We're saying even stronger, right? Because Pareto is bigger, right? Core is smaller. So it's a much stronger concept. We say strengthened first welfare theorem, right? Probably the second thing probably you would want to say is it possible to say more, right? Because second welfare theorem said what? All the Pareto efficient can be done by Lavoisier equilibrium by moving around the endowment. Can we do the other way around, right? Is it any core can be done by Lavoisier equilibrium, right? That's something we care. Or some manipulation of that. And turn out that this is not possible. But there's a very famous theorem, turn out to be something very interesting, is to qualify is when the economy is big enough, getting bigger and bigger, more and more people, which we define precisely, this core shrink. And at the end, you go to infinity, the core and Lavoisier are the same. Okay? Let me repeat the statement. Although we cannot make every core to be implemented by Lavoisier equilibrium, but the way we do is we make the economy big. Okay, we will define precisely because how to define big is we increase number of agents in society, getting more and more and more and more people. Okay, we will define precisely what does that mean, but this core will getting smaller and smaller. At the end, they coincide. The core consists only one element, is Lavoisier equilibrium. So that is very strong. It's very strong because Lavoisier equilibrium doesn't include anything about price. What it says is, as long as the economy is big enough, no one is allowed to go away. No one can go away, right? Then the only outcome you get is Lavoisier equilibrium. Very strong, right? There's nothing left there, right? There's nothing, only one thing. But of course, we'll define what do you mean by getting bigger, which we'll make precise now, okay? But do you get the main concept here, right? First thing we do is we say a much stronger first welfare theorem, which we said core, the Lavoisier will be in the core, right? First welfare said Lavoisier is Pareto efficient, so it's stronger, right? Second welfare said every Pareto efficient can be implemented by WE, right? So that's why somehow this is the same thing, right? But the core, we cannot say every core can be done by Lavoisier equilibrium. We can't do that. But we can do other way around is string this thing by making and they are coincide. That's called the core convergency theorem. How to do that? Let me do it very quickly. because it's not something. Okay. What do you mean by get the economy bigger, right? Because we have n agent, each one is very different. They have endowment. How do we say economy bigger? So what we call is a replica economy. Okay. So replica economy means the following: simple. Suppose the economy consists of all of us. How can we add more people? It's going to add you, add me, or add your friend. It's very simple. It just double us. Make a copy of us. So you have 2 of me, 2 of you, 2 of your friend. They will call 2 replica economy. If 3 replica means 3 of you, 3 of yourself, okay? Copy yourself, okay? And we have 3 double endowment, everything is double, okay? And that set is when you go to infinite replica, the core is exactly the Lavoisier equilibrium. Okay, that's one of the most important results in this general equilibrium, right? Because no matter what system you're using, okay, I don't care about what system you're using, as long as system is immune to collision blocking. Okay, you want a system that no one wants to go away with the resources. Okay, you want a system stable. The only thing you left is Lavoisier equilibrium. So market actually give you the thing that is nice. Okay, when the market is large and it's stable, right? If you want have a globalization, you want a lot big economy, you want thing to be not changing, stable, that is what you get, right? In some sense, it explains why globalization works, right? Because when you scale up, it doesn't break down. Okay? And there's only thing you can converge to. Okay. I don't have time to talk about more, but beside core, there are many other concepts like nucleus, kernel, whatever, bargaining set, or everything we've got a similar result. There's some way to convert, some way to include. So Lavoisier equilibrium is a very nice result. If you want, you have to study the 4 to 5 chapters in Masco, Lewis and Green. They spend a lot of time to prove all those kind of technical results. Okay. So I have 1 minute left. So first thing is when production, what happened with chapter 2? No problem. Everything goes through nicely. As long as firms are price taker about the perfect competition, right? When you have oligopoly or monopoly, everything dies, right? So no monopoly, everything doesn't work, right? And what about uncertainty? Well, quickly, actually, that's what the finance people were actually doing, right? Because we have overtime, you have uncertainty. How can we do about that? First, uncertainty. How can we do that? Actually, we do in next class as well. What we call is invent some what we call the contingent good. Okay, is instead of talking about uncertainty, we talk about state of the world. Okay, you have say umbrella in the good sunshine, umbrella under rainy days, umbrella under cloudy, and as long as all these goods are traded, right? If they're traded, their price, then everything would work, no problem. Okay, but of course, does this market exist? No, right? You can't trade every uncertainty, so that's an issue here. So that's why, right? Even when you have symmetric uncertainty or whatever, that's fine. But when you have asymmetric information, everything fails. Okay. And here is the idea is if you can't trade with every uncertainty, that introduction of the time, you allow sequential trade over time, right? Because the reason is being that you can't, at the beginning, you know what happened at the end of the universe, right? The problem of contingent market is this require you trade every contingency, right? So you have to trade rainy tomorrow, rainy the day after tomorrow, rainy every day until the end of the world. There's no way you can trade every commodity, right? But if you allow people to keep trading over time, okay, that actually you are able to reduce the number of contingent good, okay, needed, okay. That means that if your stock market, in some sense, stock market, they keep trading, you don't need a lot of security to trade, then it's feasible. That's why you can define what is the stop, what's the option, how do you define that actually can be done, okay. But that would be too complicated to cover in our class, okay. And that you will learn if you learn the finance class. So finally, I would like to highlight this program of the general equilibrium actually kind of fails. That's why I don't cover too much, because of a rise of the three things. If your business good, you know very well, right? First one is information asymmetry, right? Because the lemon market, right? Because I don't know the second-hand market, I don't know the good or bad, I don't want to trade. The market collapsed completely. So that doesn't exist Mawassan equilibrium. The second one is transaction cost, okay? Externality is an issue because we can't really contract those stuff. Okay? How to define property rights? How do you enforce? Very expensive. So market doesn't exist. Lastly, it's called incomplete market, which you have highlighted already. You have uncertainty, right? You want to trade for every contingent, but you can't really do it. Okay. So that's why it's not efficient or constraint efficient, right? Because there are a lot of things you can't really trade, right? You cannot hedge the risk that you get F from this class. There's no market you can buy an insurance so that you make sure that you get an A, right? No one bet for you for that, right? So this doesn't exist. So that's why you can't really do any market on that one. So that's why we'll do it in the next class, okay? And as we said, next week we have holiday. So I will see you 2 weeks later, right? Because next week is October 1st, right? So we can't really have a class. But remember, your homework is due October 3rd, 2 days after the holiday. So anyway, have fun. I will see you in 2 weeks' time. Bye-bye.